Sorry. So let's go ahead and look a bit more at how we can use morphological data in order to draw these trees. So when we look at different character traits or characteristics about a species, we can make what's called a character table. So if you see a character table like this, what that's saying, like here I have species 1, let me put that pointer on, species 1, 2, 3, and 4, and if I were to record different like characteristics about them, if you have like a check mark or a plus sign or an X, this basically is telling us those traits are present in that species. So when you have like, here we have these 2 or these 3 like black feet or a white head stripe, these are called shared derived traits, and they're used to group organisms. So you can see like in species 1 right here, it does not have black feet, but the other 3 do. So like black feet can be used to group those 3 together, and that would imply like those 3 are separate and have a like a common ancestor that had black feet. And then if you look at species 3 and 4 with that white head stripe, that's unique to species 3 and 4. So they have, using that information, you would group them more closely together as having a common ancestor with that white head stripe. So when we build these trees, though, you can build them, when we use morphology, we're basically going off of the fossil record. And one of my favorite examples is the evolution of horses. And we can see that through the time in the fossil record, you can see how the evolution of horse size as well as legs and teeth have changed. And so when you look at the fossil record, though, you can see those transitional fossils. Like up here, you have a horse maybe 50 million years ago, the ancestor to modern horses, with 4 or 5 toes per foot. And then as you move through time, the size of the horse increased as well as their feet. So you can see in the fossil record, and when you read the fossil record, you have different like time periods written on the left here, and the older rock layers are near the bottom and the more recent are near the top. And so you can infer age and time based on those rock layers. But another type of evidence we can use is called the molecular data. So sometimes molecular data can be presented to you as a number of differences in DNA, or it can be presented as number of different amino acids between 2 species. So if I were to like look at these species here, I kind of like already made the differences in different colors for you. But when you interpret them, like if you compare the chicken DNA sequence to the penguin DNA sequence, there are 3 differences. But if you compare the chicken to the lizard, you can see that there are 6 differences. And the chicken to the newt is 15 differences. So when you think about like what does that mean? It means the chicken and the penguin have a longer shared history because they've only been separated for a shorter amount of time with only 3 differences between them. Now the chicken and the lizard have 6, which means that their common ancestor was further back in time, and then the chicken to the newt have the most. So if you were to draw this phylogenetic tree, you can see the chicken and the penguin would have the most recent common ancestor, then the lizard and the chicken have more differences, and the chicken to the newt. You can see here, when you look at the newt, it is the most different compared to all of them. So that means that it has been separated the longest from the rest of the species. So its common ancestor with the remaining 3 is further back in time. We would consider our newt the outgroup. Okay. Now when we draw trees, I also want to point out that like if we use this one on the left with moss, fern, pine, and rose, this is not a ladder of like less evolved to most evolved. The moss and the rose have had equal time evolutionarily to evolve. Like modern mosses and modern roses have been like, it's still present day between the 2 of them. The roses are not more advanced. It's not a ladder when we look at phylogenetic trees. They each have their own evolutionary history with different mutations and traits being selected for or against, different genetic drift, just different histories that shaped who they are. And so with that, it's not really accurate to say the moss is more primitive than the flowering plants. Also, to point out, if you really look at these two trees, you can see that they are equal with what they're saying as far as common ancestry and the evolutionary histories of these species. So I mentioned a few minutes ago with the newt, when we talk about like reading one of these, so this question asks, let me just put this here maybe, what are some shared derived characters between lungfish and mammals? So you can follow this lungfish back as well as mammals, and you see that some shared traits between them would be lungs as well as vertebrae. But you can see here this amniotic egg is not in the lungfish line. This amniotic egg would be with lizards, birds, and mammals. Being able to see UV light would be in lizards and birds only. And then you can see here we have what's called an outgroup. An outgroup does not, like, it basically can be used for comparison, but it is like an organism, part of a tree that doesn't have a lot of shared derived character traits with your in-group or what you're studying. So here we have like organisms with an exoskeleton, but if you look at the rest, they all have vertebrae. So this would be your in-group. Okay. So if you were to start simple with like different candies, here's how you could draw them. You could draw them in two styles. This is a cladogram where you have milk chocolate as a trait that you find in all of them. That'd be an ancestral trait. And then like nougat would be a shared derived trait between the Three Musketeers, Milky Way, and Snickers. Caramel would be in the Milky Way and Snickers, and peanuts would be unique to Snickers. But if you prefer drawing it in this way, this would also represent the same thing. Okay. All right, I think that's, well, we can maybe keep going. If you were to add more candies to this, I wanted to point out, like the Baby Ruth here has, if you look at like its ancestor that maybe had milk chocolate, and then it has in common caramel and peanuts, but it doesn't have nougat. So sometimes species can lose traits. And, oh, I spelled it wrong up here. It's okay. So for example, we have these like fish that live in caves who have eye sockets, but no eyes. So that eye socket is called a vestigial structure, meaning that it's like a structure or a piece of the body that serves no purpose, but had a purpose in the ancestor. So these fish actually have eye sockets, implying that showing that their ancestors had eyes, but today they've lost their eyes living in pitch black caves. Was actually an evolutionary advantage to when a mutation showed up to turn off gene expression for eyeball development, because now it's you're not wasting resources building eyes you can't use. So it was actually selected to lose eyes. And then you can also see here, I like this, how you have peanuts in the peanut M&Ms and peanuts in the Snickers and Baby Ruth. Sometimes you want to go with the simplest explanation possible. So if you think about peanut M&Ms, is it likely that peanut M&Ms branched off of Snickers and then all of a sudden developed a candy shell, lost their nougat, lost their caramel, and had a round shape, all because peanuts was here? Or is it easier to explain that peanuts evolved twice? So this idea of the simplest explanation is probably what happened. We call that maximum parsimony. And so traits can evolve twice or 2-3 times and not be due to common ancestry. For example, being warm-blooded, an endotherm or endothermic is unique to mammals and birds, but it wasn't in a common ancestor between mammals and birds. Like being warm-blooded evolved twice in evolutionary history. Okay, so let's go ahead though, and so here you could try a character trait with these. I'm using plus signs to show that they have the trait. You could add negative signs saying that they don't. So when you draw a tree for this, if you were to like write in the different species, you could try that out on your own. Oh, looks like I don't have the answer showing up for you. Okay, a couple of different practice ones. So at this point, you can practice at home. I would look at one of these and then check your answer on the next section of the video. So here's a good practice. Okay. For my students, you can go ahead and use the Google Slides to continue practice at this point.